So this video refers to Lecture 9, which is looking at centroids and centres of gravity, and it's the first video in this series for Lecture 9, and it's thinking about locating a centre of gravity. So a centre of gravity, if you imagine a shape that's not a simple shape, so an unusual shape, then your centre of gravity is often shown as a point labelled with a G. And if we were to want to use the resultant weight of that shape, then we would display it acting at our centre of gravity. So our weight, or our mass times gravity, would act at our centre of gravity. And it's very useful to be able to identify where that is, because if we're using a resultant force as part of a larger question, if we want to put the weight at the centre of gravity, then we need to know where the centre of gravity is. So in the lecture notes for Lecture 9, there's a series of equations. If you look on slide 7, you'll see there's an equation to find the x-coordinate. So for the centre of gravity, the x-coordinate would be shown like that, x bar. Similarly, the y-coordinate would be y bar and the z-coordinate z bar. And the centre of gravity, the x-coordinate would be the integral of x with a tilde on top, that wiggle is a tilde, dw over dw. So what we're saying there is we're saying the x-coordinate of our centre of gravity is going to be the central location of the piece of it that we're considering. So we're going to integrate, we're breaking down into very small pieces. X tilde is the centre of that piece, and I admit I've missed the centre of that piece there. dw is the weight, and obviously the integral of dw is the weight of the whole object. And for y, you'd use y bar and y tilde. For the z coordinate, if we're doing 3D, you'd use z bar and z tilde. And if we replace our w's with m's, so for instance finding the x-coordinate centre of mass, which will be the centre of the shape's weight as well. So to find the centre of mass, we do exactly the same thing, apart from we're using dm instead of dw. And we can do the same thing looking at replacing with dv and find a geometric centre. So to find a centre of gravity, we use our top equation. To find a centre of mass, we use our bottom equation. For this just being the x-coordinate example I'm showing you. And for a centroid position, a geometric centre of a shape, we would replace that with a dv of volume or dA in area, depending on if it's 2D or 3D. If you look at slide 9 of the lecture notes, there are some common centroid positions for some common shapes. So, for instance, you know a rectangle. The centroid is halfway in the height and halfway in the width and halfway in the height. So, x bar is going to equal width over 2. That's a fairly easy one. On the website and through Blackboard, you can access a lot more common shapes, and they'll also be in the exam paper if you require them. Quarter circles, semicircles, circles, and it tells you where the x bar, the y bar position are, and it also tells you how to calculate the area. But if we go on to look at the example that begins on slide 11, I'll just briefly sketch it and then I'll talk you through it. So we're asked to find the area of the bit that I'm just shading in now. Okay, so we're asked to find the area of that shape. What we're going to need to do, if I just remove some of those lines, this bit I've just shaded in, is still a bit we're interested in, I just need to sketch onto it. We're going to find a series of different pieces of information. So we know that, for instance, the x bar coordinate is the integral of x tilde dA over the integral dA. So we're going to consider, if we're integrating across this length, we're breaking it down into very, very small strips. Each of those strips is a width, dx, and is a height, y. And the centre of that strip will have an x coordinate and a y coordinate. So the centre of that strip will have x and y coordinates, x tilde and y tilde. And we know that the y coordinate, y tilde, is going to be y over 2, because it's halfway up that strip. So if that's y, the centroid position of just that strip that we're breaking our shape into when we integrate will be y over 2, will be just there. So what we now need to do is we now need to take the three terms from our equation and start putting them together. That should be a tilde, sorry. Well, if we're considering integrating this whole shape, we're going to take this strip, which is of width dx, and we're going to move it all the way along. So wherever our x position is, our x tilde will just be a position x along the shape, and we're going to move that along the shape, obviously, as we integrate. So our area is going to equal, for that rectangle, y, the height, times the width, dx. Well, y, we're told for this line, is x cubed. So that's the same as x cubed dx. Our x tilde position, we've already said, is x. Our y tilde position, we've said, is y over 2. And y is x cubed, so it's x cubed over 2. We can now start substituting things into our equation. First of all, for the x bar position, so we've said x bar is the integral of x tilde dA over the integral of dA. So the integral between 1 and 0, because this is 1 metre, we're moving our strip 1 metre in distance, and we're going to do the integral of x tilde, which is x, dA, which is x cubed dx, over the integral between 1 and 0 of dA, which is x cubed dx. It's the integral between 1 and 0 of x to the 4 dx over the integral between 1 and 0 of x cubed dx. Jump to the next page. That's going to be x to the 4 becomes 1/5 x to the 5 between 1 and 0 over a quarter x to the 4 between 1 and 0. Substitute 1 into there, and I'm going to get 1/5 minus 0 over a quarter minus 0. That equals 0.8. So our x coordinate of our centre of that position, our centroid location, our geometric centre, is going to be 0.8 metres in the x direction. So somewhere about there. So now we can go on and find our y position. So our y position, y bar, for the whole shape, is going to be the integral of y tilde dA over the integral of dA. Well, the integral of dA we already know, because we've already worked out in the previous section, is just that, a quarter. So we don't have to do any more calculations on that. The other part we're going to do is y tilde. Well, y tilde, we've said, all the way back here, is x cubed over 2. So x cubed over 2, apologies I've left this in green, and dA was x cubed dx. Looking for the integral. Now, jumping back again, apologies, but we're still moving with respect to x dx, so we're still moving between 0 and 1 in this direction. So we're still between 0 and 1 because this dimension here is still 1 metre. We don't need this y dimension at all in this question. that's all over a quarter. If I then start multiplying that out, that's going to be the same as the integral between 1 and 0. In fact, I've missed that one there. The integral between 1 and 0 of x cubed, of x to the 6, looks like x to the 36, sorry, x to the 6 over 2 dx over a quarter. So that's going to be x to the 7 over 14, 2 times 7, so 1 and 0 over a quarter, and that's going to equal a 14th, 0 over a quarter, that's going to equal 0.2857 metres. So that's how you would find the x and the y coordinates, the x and the y position of your geometric centre, your centroid position for that shape. There is now a group problem solving exercise that's related to this, which begins on slide 14 of the lecture. You have a go at that question and then come back to these notes. I'll show you how to go through it. So this is the group problem solving exercise began on slide 14. You have got a little bit more information because you're actually looking for the reactions at the supports A and B as well. But if we first locate the centre of mass, and then I'll talk you through the last bits, although the last bits should be a little easier, a little more familiar. So first of all, we're going to break our shape into very thin rectangles again, i.e. we're integrating. Okay. However, our integration is slightly more complicated because there is a line, a function, y squared is 2x and y equals minus x at both ends of our rectangle. So our area is going to be y2 minus y1 times dx, because the width is still going to be dx, so this distance here is dx. y2, well, at the top we've got y squared is 2x, so y will be root 2x. So at the top we're going to have root 2x, and that root is across everything, and that's going to be minus the bottom, and y at the bottom is minus x, so minus x dx, root 2x plus x dx. X tilde is just going to be x, it's a position along the x-axis that we're moving that rectangle at any one point. And y tilde is going to be the average between the top and the bottom. The middle is going to be between the top and the bottom. So it will be y1 plus y2 all over 2. So that's going to equal root 2x plus minus x all over 2, which is root 2x minus x over 2. So now we've got our dA, our x tilde and our y tilde, we can solve this like before. So x bar is going to equal the integral. This time we're working between 0 and 2, because the distance is 2 meters, of x tilde dA over the integral between 2 and 0 dA. So for this particular question, that's going to be the integral between 2 and 0 of x times root 2x plus x over the integral between 2 and 0 of root 2x plus x. Might be helpful to remind people that root 2x is the same as root 2, where the root is just over the 2, x to the power of a half. So if we then start to integrate that, well, first of all you're probably going to want to multiply some things out. So root 2 x to the half times x is root 2 x to the 3 over 2 plus x times x, x squared. You're still going to want to integrate that between 2 and 0. That's all over the integral between 2 and 0 of root 2x plus x. So if I raise that by a power, I'm going to get root 2 x to the 5 over 2 divided by 5 over 2, so that's the same as times by 2 over 5, plus x squared raised to the power becomes x cubed over 3 between 2 and 0, all over root 2 x to the half raised to the power becomes x to the 3 over 2 times 2 over 3 plus x squared over 2 between 2 and 0. If I substitute my 2 and my 0 in, I get 5.867 over 4.667, which equals 1.257 metres. So my x coordinate for my centroid position is 1.257 metres. And if you remember, we don't now need to do this bit again for our y-bar coordinate because we already have it. Looking at the y-bar coordinate, that's going to be the integral between 2 and 0, because we're moving in the x direction. In the x direction it goes from 0 to 2 metres. Y tilde was root 2x minus x all over 2 root 2 times dA, which was root 2x plus x dx, all over 4.667, which we calculated previously. So if we deal with just the top part, and I'll put the 4.667 back in at the end, well, that's the same as the integral between 2 and 0 of a half brackets root 2x to the half minus x root 2x to the half plus x dx. And if we then start to multiply those out, we're going to get half root 2x to the half times root 2x to the half becomes root 2x, that root just being over the 2, minus x times plus x becomes minus x squared. Root 2x to the half times plus x and root 2x to the half times minus x will cancel out, and put our dx. So I've just multiplied out that bracket. If I then integrate that, I'm going to get half times root 2 x squared over 2 minus x cubed over 3 between 2 and 0. And if I put my half back in, I do need to make a small correction. When I multiplied root 2x to the half and root 2x to the half just here, I should have got x, but root 2 times root 2 just comes out as 2. So that root there and that root there should go. Apologies about that. If I then multiply my half out, that's going to give me x squared over 2 minus x cubed over 6 between 2 and 0. If I substitute 2 and 0 in, I'm going to get 0.667, and remember all of that needs to go over the integral of dA, which we know is 4.667. So my final y bar, my centroid coordinate in the y direction, is 0.143 metres. And that concludes the group problem solving exercise for lecture 9 that began on slide 14. But Oh no, it doesn't. No, there is more. That concludes the centroid part. However, there is an additional part to this question. We're asked to find the support reactions. So all the way back in our original question, we now know where our force sits. So we now know we have a weight acting here, and we know our x direction is 1.26 metres, and we know our y direction, which I haven't drawn very big, but is 0.143 metres upwards. So now what we need to do is calculate our support reactions. Well, first of all, we need to calculate a weight. So our weight is going to equal our mass. But we don't have mass. We've got an area. We've got a thickness of the plate. We've got a density, which is in kilograms per metre cubed. So we've got number of metres cubed here. Kilograms per metre cubed was 7,850. And that will give us a mass in kilograms. So we now need to times by 9.81 to get a force. So we've got volume, we've got density, we've got gravity. Sometimes your densities will give you a Newton per metre cubed, and you don't need the times 9.81. So our weight is going to be 107.8 kilonewtons. We can then look back at our diagram. I'm going to quickly sketch it again. So that's a very quick sketch of our diagram. There are three forces that we don't know. This pin joint here will have an X and a Y force associated with it, AX and AY, and the B joint down at the bottom will have a reaction force associated with it. There'll be nothing in the slope parallel to the y equals minus x slope, because it's a rolling joint. So we now need to use our equations of equilibrium to calculate our unknown forces. We've got two unknown forces at point A at the pin joint. So if we take our sum of our moments about A, we can ignore both of those. And that leaves us our normal force B, which is just here. And that will be multiplied by 2 root 2, which will be the perpendicular distance or the length of this line just here. So if we know that's 2 metres and that's 2 metres, then this will be 2 root 2 metres. And then we've got that force. We've also got our weight, which is 107.8, and that perpendicular distance from A is going to be its x position, 1.26 metres, and that all has to equal 0. Apologies, I can't get that on the same line. We can rearrange that. We can find our contact force is equal to 47.9 newtons. We can then do some of the forces in the x and the y direction. So we're going to have minus AX plus 47.9 sine 45, and we know it's 45 degrees because we've got 2 metres there and there in the x and the y direction, and that equals 0. So AX is equal to 33.9 kilonewtons. And finally, in the y direction, we've got AY, we've got 47.9 cos 45, and we've also got the weight equaling 0. That's meant to say equals 0, apologies. So AY can be rearranged to be 73.9 kilonewtons. That really does conclude the Centroid's question group problem solving exercise in 2-dimensional. So that concludes the first section of locating centres of gravity in centroids. There are a couple of other videos that go along with this that conclude lecture 9.